Okay, so sorry we don't have full space stuff, but we're gonna talk about GPUs. Sort of to set the stage, the justification, like models, especially like large language models have gotten like huge, and now we can't even load them on our GPUs because we don't have enough VRAM, right? Especially for fine tuning, stuff like that. So there's a technique called gradient checkpointing, where what you basically do is for some layers, instead of how like when you do a whole forward pass, you have to say well autograd saves all the intermediate gradients, and you do that to compute the backward pass. But instead of doing that, like in between two places of computation, we just discard everything, every intermediate gradient. And when we do the backward pass, we only save the input at that point, the intermediate input. And once we get to the point where we need the gradient there, we just do the forward pass again. How does that make sense? So we have like some checkpoints, bam, 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 bam. There's the whole model. Once we do the forward, we go back, we do the forward again to this point, and then do the forward this little segment of the model to compute the gradients. That way we can sort of chunk the computation in a way that we have enough memory to use it. So our experiment really was like, how much should we checkpoint in like a model? So we use Quen 1.5 billion, right?
Yep.
And the trade-off here, of course, because we do extra forward passes, then it'll be slower. There will be less tokens per second, right? But surprisingly enough, uh, of course, doing full checkpointing in every single layer, it's the slowest, but the trade-off is huge, as you can see in this graph.
We have a large increase from uh, like recomputing everything to like recomputing every other block.
Right. So to explain this graph, the y-axis is so in the red line is the maximum gigabytes of VRAM that we're using, right? So ideally, we don't want to get more than 100 something gigabytes, because then we get out of memory. And for the yellow line is how many thousand of tokens per second in average the model takes, right? So we see, and the x-axis is sort of the checkpoint frequency. So one being we checkpoint every layer, two being we checkpoint every two layers, so on and so forth. So we can see like uh, checkpointing every layer reduces the VRAM by a lot, like what is it, like by a factor of 3, while we only have like the slowness that it produces if we do checkpoint. It's probably worth it. It's about 3,000, right? Mm-hmm. Right. Yeah. So
down to the tokens.
right. Yeah. You want to share the other graphs?
Yeah. So something that might be a little more visually appealing is looking at sort of the memory footprint of these processes.
In one single run.
Yep. So we did some memory profiling, and you can see like just the little intricacies here of if you're like recomputing everything, we get these.
So this is checkpointing every single layer. You can see how the memory footprint is pretty low
Yeah.
overall. And then if you compare it,
there's like 12 layers, right? So
right,
so there's like
12 little spikes. Yeah, of every like intermediate forward pass.
What are the big spikes over there?
That's when we calculate the loss, right?
Yeah, this one there's over technical loss.
Like the whole loss of the model.
Oh, so it's like the final
Yeah.
layer of the model.
Yeah, exactly. So that's and it's just 20. Yeah. So that big spike like stays constant over all the runs, but if you can see like on like this is the big spike that we see here, right? So here our maximum was like 95 gigabytes. Like this is if we do the gradient checkpointing every two layers, right?
Yeah.
Yeah, every other block.
Every other block. Yeah.
Uh-huh. So this spike right here is the same as this spike, right? So it's very tangible, the difference.
Yeah, but you can see like the memory footprint
Right.
here gets quite large.
Yeah, and if we don't do gradient checkpointing, we can't even run the model or for fine tuning because we just don't have enough memory. And this is with a huge like what was it, like 120 gigabytes of VRAM, which is much more
Yeah,
than
so
anyone.
it's not just quantization, folks.
Yeah.
Okay, gotta mess with the techniques.
Yeah.
What are you using for your model trainer? Like, did you roll your own or?
We use some like harness code that was given to us to like fine tune.
Yes, it's just
So it instantiated like PyTorch.
boilerplate fine tuning code.
My comment would be, so you're training on batch size like 1 or 2 on 1.5 million parameter model.
Right.
Okay. It should not be taking 95 gigabytes ever for memory usage at some point. It's usually that the math works out to it's about 12x the number of parameters is the full fine tuning memory usage. So yeah, it's like you can fine tune it on like a 3090, like 24 gigabytes of VRAM at batch size 1. Would be my guess. So my thought is that I think there's a bug somewhere in your training code. Because yeah, the utilization numbers are way too high.
Well, it is around 40 gigabytes if we do full gradient checkpointing, which is what most people do now.
That's without any gradient checkpointing.
Without any gradient
It's without, yeah, when you introduce gradient checkpointing back in, I think you can reduce it by about a factor of 2. I don't know if you guys looked into it either as well. Sorry.
No, you're good.
But, for gradient checkpointing, usually what you do is it's selective gradient checkpointing, not on a per layer basis, but on a per operation basis.
Right.
So like for instance, like dense matrix multiplications consume the most amount of compute, but then stuff like layer norms is very easy to compute.
Right.
And so you will selectively recompute layer norms and other easy operations. But the dense linear operations, you won't, you'll keep those in memory. And so that's what people tend to do. And you get like 50-ish% less memory usage than you would from your gradients.
There's gonna be more research events.
It's gonna join today.
Oh, yeah.
That's a good question. So if you train on 60,000 say transformers with like PRL as a trainer, you'll go up to 1.5 million model.
That's, I guess, yeah, what sequence like you're trading on?
Yeah, so
That's something I guess the numbers I have
key.
I think for sequence. Okay.
yeah,
Then it's 4x more, so yeah, that would be about it. Actually,
Yeah.
it's well, so yeah, what sequence? Yeah, that is true. Yeah,
That was neat. I guess like that's what you researched one of the previous Sundays, right? That like you can chunk the final logics layer in the pre-connected
Yeah.
maps
No,
like
no.
this to
If
drop
we
the
have time, I can talk about that. Yeah.
Yeah, that's the other.
I think this is already using some tricks to. But yeah.
Mhm.
Okay.
We still see spike.
we still see the final logic
Yeah.
spike to the giant. Definitely need to chunk them further.
No, but I also did the profiling of Hackathon transformers. That one is done.
What do you mean? It's
Like basically like if you you can put one batch with 16K, it's fine. I think the limit is about 20K plus between 25. Here is still some memory that you don't put on. It's the demo.py.
Yeah.
It's a super labor question. Just want to check what is a checkpoint is.
Yeah.
What is a checkpoint exactly?
Yeah, so the naming is a little tricky. It's not like you're saving the model. Like checkpointing means for a given like subsection of like the computation graph, we save the input, like the start of it, but not the intermediate gradients, right?
Very confusing.
So when we do the backward, we have that saved input to do the forward, right?
Yeah.